Last lecture we finished at this position here. We discussed that it's very likely from what we have learned about the statistical proofs or the statistical analysis that temperature, global mean temperature, and the concentration of greenhouse gases are highly correlated. And we also made some statements why this should be for physical basis for this. And so now we come to the problem that actually since maybe more than 20 years the community dealing with climate, interested in climate, tries to they don't call it predictions, but they try to do projections for the next, let's say, 100 years. So we try to understand what may be the mean climate in 100 years, just to understand what is the future, quite from the Earth's perspective, very near future of our climate. It's a very important question, but obviously very difficult to answer for the various reasons that we will maybe discuss now. But what we know is that the greenhouse gases, they warm the surface temperature. They increase the surface temperature of the Earth. That's what we know. And greenhouse gases continue to increase. And the many estimates for the next 100 years would estimate very likely a doubling of the CO2 concentration. Something more or something less, depending really on what is the development of society, of economy, and of the Earth population, obviously. It depends how many we are and what we use per head, if you want, and what industries are using as fossil fuels, how much fossil fuel we get out of the Earth and burn it in order to understand how much greenhouse gases will increase. And CO2 is not the only one. There are other greenhouse gases that we have discussed. Water vapor, obviously, but it's very difficult that we influence this. Methane is another greenhouse gas. But the most important one is perhaps the CO2 that we increase by fossil fuel burning. There's very little doubt that this will increase in the next years. And whenever there's these reports appear like every 4 to 5 years, a new assessment of the climate community on what is the likely development in the near future of the greenhouse gases and of the Earth's temperature. And whenever there's a new report, actually it seems that the CO2 increase in that few years was larger than was estimated by the previous report. So it's not that even though we are aware that greenhouse gases may cause this imbalance to the Earth climate, still humans are producing more of it than is maybe estimated in the worst case scenarios. So there's no question about this. There are other things that are, of course, deforestation, maybe also still an interesting and very important topic and is relevant to climate because, again, as we have discussed, we deforest, we likely burn the wood, and that increases the greenhouse gases and causes also other changes to the climate system. So the Earth climate will be warming due to this. There's very little doubt about that. I repeat this a few times. There may be 95% of climate scientists who believe that the Earth will be warming in the next, let's say, on a very slow time scale. We cannot talk about from 1 year to the next because that's a too short time scale for something to see. Also, because other kind of variability may interfere with this. But let's say if you do like an average over 20 years, then it's very likely that in a 20-year time period, the Earth will warm, even for the next 20 years. There's a minority of scientists who have also their own beliefs that maybe, for example, due to solar radiation changes, they believe they have some estimate what solar radiation changes may be in the next 20 years, actually the Earth's climate may be cooling. But this is a very minor community who still believes in this. So there's a kind of a broad consensus for physical reasons and for what we see, what is happening right now on the Earth, actually, if we look at the observed record. Yes?
Is there any percentual estimation about how much is the CO2 contribution by the deforestation?
They are. It's by far like more than 90% perhaps, a number that I just take out of the pocket here, fossil fuel burning. The deforestation is probably more important for other things, because if you deforest, you really change the regional climate completely. You know, you redistribute rainfall, you change the surface reflectivity, you change the regional climate completely. It's probably a little bit less relevant for the development of the CO2 concentration in the atmosphere. It's a small contribution, but it's mostly fossil fuel burning. But they're estimates, but I'm not able to tell you the exact percentages. But it's by far more important what amount of fossil fuel we are burning. So what will happen in the next 100 years? And there's this, I think this is quite nice. It's tough to make predictions, especially about the future. You know, whoever tried ever to make predictions, what happens in the future, will know that this is actually either it's trivial. You know, one prediction is trivial. It's trivial for our regions here to say that in July it will be on average warmer than in January. And in the next lecture that I will be giving, we will discuss the seasonal cycle, what is happening in the seasonal cycle, and we will understand. You all know why this is the case, essentially already, but we will discuss this in more details. So there are predictions that are very safe. The average temperature in July will be higher than the average temperature in January in this region. In tropical regions, may not be the case. And in the southern hemisphere, of course, it will be the opposite. But for Trieste, for example, we know mean temperature in July will be higher than mean temperature in January. But that's a trivial thing, because we know that every year the Earth rotation path and the Earth tilt with respect to its own rotation axis is the same, or more or less the same. And so there's no doubt about this. So trivial predictions are always possible. But to predict something that is a real prediction based on the physical system, based on the Navier-Stokes equations, on the thermohydrodynamic equations that we have been writing down in the first lecture, that is a much more difficult business. And we all know for theoretical physics, weather forecast, the ability that we can do weather forecasts is a big success, because the equations are so complicated. And still we are able to predict nowadays the weather in this region. In tropical regions, again, maybe slightly more difficult, or in some cases easier, depends. But let's say in this region here, we are able to predict the weather for 5 days, quite accurately. So if you look on the weather forecast for Trieste, up to 5 days, there may be some skill in it. You will find that they are quite good. And this is because over the last 50 or even 100 years, these models have been slowly developing. People found error. And so every day you can check, has the forecast been right or not? There are many forecasts. So you can do many good statistics with all these forecasts. And models have been improving continuously throughout the time. And for weather forecast, this is very easy, because every day you have a new point in your statistics. Oh, this forecast has been wrong. Why? People try to investigate, find an error in the model, improve. And slowly this goes on. So for weather forecasts, that's a very good situation. We have a history of maybe 50 years of repeated weather forecasts. So 50 years times 365 days on average, or something like that, close to it, is a large number of statistics for any region of the Earth. So we have a good statistics there. We are able to do this. Another thing is seasonal forecasts. There are also people are trying to do seasonal forecasts. So not only for the next 5 days, but maybe for the next 3 months. And those are trivial to say, okay, January will be colder than July in the Northern Hemisphere, in most regions of the Northern Hemisphere. That's a trivial thing. But a real forecast would be if we predict now that in July or August we will be warmer or colder than the average. Like if we look at the average from every year, will it be slightly warmer or slightly cooler than the average of all the years that we have been observing in the last 50 years or so? That would be a real forecast. And those forecasts are actually much more difficult and much worse, obviously, than a 5-day forecast. They are also based on the same equations. The same models are used to make those forecasts for the next 3 months. But as you can imagine, other things play a role there. Very slow changing ocean surface temperatures, and we will discuss this hopefully also today, play a very important role, for example, in the seasonal prediction. Still there we have each year, let's say, each year we can have 5 or 4 or 5 seasonal prediction for each consecutive month. Let's say 12. So, but the number is obviously already very much reduced with respect to the numbers of weather forecasts that we can do each year. So already seasonal forecast is a little bit more tricky, but again, there are problems due to the fact that we do not have so much data to improve our models, to test what has gone wrong in this seasonal forecast and what was okay. And the other problem is that the predictability may be lower. There's an inherent limit in the predictability of the atmosphere-ocean coupled system. So both are problems. Now we come to the next problem for the next 100 years. So essentially, here we are really in trouble because for the observed history, not even we have 100 years of good data. We may have 100 years of medium good data until the 1950s, and then from the 1950s onward we have quite good data. So let's say we have 100 years of relatively good data. Depends really where we are looking and what we are looking at. And we try to test our models on this one data set. As you can imagine, it's very difficult to do that. You cannot really test the model. All the models that, we have seen how the global mean temperature develops in the last 100 years. If this is temperature and this is time, and here we are at 1900, and maybe here at 2010, and then the temperature somehow moves up like this without looking at the details. So it goes slowly up as we expect, determined by the slow increase of the CO2. And obviously, climate models will be able to reproduce this curve. So it's no problem for climate models to reproduce this. But then many scientists are working on that. So they're able to, we call it, adjust parameters in the model. There are so many kind of not strictly physically based parameters in these models, but we call them parameterizations in these models, where parameters are kind of based on the turbulent behavior in the boundary layer and things like that. That it may be possible to adjust all these parameters to get this curve right. But does it mean that we can predict for the next 100 years? From weather forecasts, we know we have tested the models. Every time there's a every day when the weather is changing, we test the models. Here we have just one. We have just one event. We can tune our model, or we can fix our model to reproduce this curve. But does that guarantee that it will predict the future right? It's a very difficult problem. Probably not. So people try. For this reason, there are many approaches, of course, that scientists do, because climate scientists are well aware of this problem. And this is only one part of the problem. We will discuss other parts in a minute. So what can we do? We try to use this proxy data that we have discussed also before, where we do not really have measurements, but we make estimates from tree rings, or we have ice core information from the Arctic and Antarctic. And so that gives us proxy, very, very little, but valuable information about the far past of the climate, and we try to apply the model there. Of course, there we have the problem that the accuracy of the data is very low. So we have a lot of freedom to adjust our model there, because if the error bar of this measurement is huge, then we can be happy wherever our model is within this curve. So it's a very big problem that climate scientists are facing there. And this is only part of the problem, because it may be possible for models to adjust this temperature, and most models can reproduce this even to some details which may be related to volcanic eruptions or other events that influence the global mean temperature. But if you look at the regional scale and compare observed climate estimates with the temperatures of what the model is producing, or rainfall what the model is producing, the regional errors, or we call it biases, are often larger than the signal we want to predict for the next 100 years. So even though climate scientists work on this, to improve this always, but often the situation is still that the regional error that the model has over Europe, over the United States, over some tropical regions, over Africa, over India, can be larger than the change signal that the models are predicting for the next 100 years. So of course, you think, okay, that could be a problem. If the basic error of the model in a region, I'm not talking about the mean temperature. The mean temperature can be fixed quite easily for models to produce the right curves. But regionally, the model can have huge errors, which are larger than the signal to predict. So this is all to be kept in mind. Still, nevertheless, people are making this effort and kind of using, you can do, for example, one thing, divide this into periods, try to improve model on one period and pretend you do not look at the other period and see if your model is doing the right thing. So climate scientists believe that their models are in some sense doing the right thing. And so what is predicted by these latest assessments for the next 100 years is, given all kind of possible evolutions of the CO2, the warming of the Earth cannot be prevented anymore. Even if CO2 increase is stopped now. So now we go back to some kind of medium level. The Earth will still warm up because it's out of equilibrium right now. So the estimated, and this is even not a realistic scenario, the estimated temperature for, let's say, in 100 years is estimated, the mean temperature, to be 2 to 6 degrees warmer than it is now. Can be, depending the extremes of the model, would be some kind of estimated from the ensemble of all these simulations. Can be, extremes can go a little bit closer to 0 here, or even extremely higher here. So 6 degrees would be huge, a huge perturbation to the climate. Because we will look at this picture later, I think. Regionally, this could mean really, really, really strong perturbations to the regional temperature. And the sea level will rise because of this. Can you guess why the sea level will rise? as kind of a byproduct. Is ice melting is one important process. The other is actually almost equally important, the expansion of water volume with increase of temperature. So even that sounds like tiny, so the temperature increase average maybe by 3 to 4 degrees, a tiny perturbation if you look at the absolute temperature. But in this range, this is enough to cause the volume of the water to increase, because we know that the minimum density is something like 4 degrees. So for these two reasons, the sea level will rise by 0.5 meter, which for Trieste is not a problem, but for many countries, maybe some countries where you are from, this is a big problem. If the average sea level is rising 0.5 meter, that could cause many problems in particularly some tropical countries, which are very close to the sea level, and also in other regions. So this could be quite problematic. But are these forecasts accurate? Yeah. The thing is, no one knows. We can only guess, can we trust these models or not? There are so many uncertainties. First one is what's happening to the CO2 evolution. Okay, we have to live with this. I would, as a climate scientist, I would say that's impossible to predict. What is the future of developments? That depends on the behavior, almost on a long time scale, let's say random behavior of governments and who would know who is the next president in the United States, which may be important for following some more restrictions to the output to the use of fossil fuel. No one knows, for example. So this is unpredictable. I think I think what climate scientists should more be concerned about is, are the models sufficiently, here we say, complex to predict climate. I wouldn't even say that complexity is the only right question here, but that's one question. Are our models complex enough? Do we include enough processes in order to be able to predict the climate for the next 100 years? And the most likely answer is no. And there are some people who criticize this, that we should do less modeling and more look at data that is already there and understand processes. Yeah, there was a question there.
I want to know if the prediction about the next subject is include the change of the universe, the evolution of the universe.
No.
Because this one also can change.
Yeah, the universe, I'm not... So I guess you are talking about a very different timescale here. Really, I mean, of course we don't... I guess the same is true here. Who knows if in 2050 a meteorite drops on the Earth, a huge meteorite drops on the Earth. We are not able to predict it now. That would invalidate all climate predictions we have done. So there are events that are certainly unpredictable, that with a very low probability probably could happen, that would make all predictions invalid, obviously, because if a huge meteorite hits the Earth, anything could happen, I guess. Predictable changes of the universe, they are on much longer timescales than what we are talking about here. So if you're talking about a changing of the output of the sun, we all know, or maybe not all know, but it is well known that at some point the sun will develop into something different and maybe will die out at some point. But there we are talking about really timescales that no one of us can be concerned anymore. So astronomical timescales, I guess the predictions in these models are probably that everything that is important for the Earth's climate is more or less constant. So the output of the sun is assumed to be constant. We know that people know that there will be an ice age approaching probably in the next 50 years, so 50,000 years, not 50 years, sorry. So you can, if the time scales of the predictions is that long, you could try to implement these kind of small changes in the parameters of the rotation axis of the Earth into those simulations. But everything else is certainly not relevant for this time scale. However, there could be events that are completely unpredictable that would invalidate all our estimates. We should mix.
Yeah, otherwise one day we can be burning this.
Okay. Yeah. It's an opinion. Another.
Yeah, okay. From the first law of thermodynamics, we can keep the internal energy of a system by letting the volume to expand, right? In general.
Okay.
And then now we have, okay, if we consider Earth and the atmosphere that cover as an envelope as our system, and then if the temperature is going to increase, and then we can keep.
We expanded.
Yeah. So that the model consider this the expansion of this envelope.
Yes. Yes, all these things are taken properly account into the equations that have been modeled.
If the rate is high, then at least we can keep the same kind of temperature.
Yeah, the thing is, we have discussed this also. I mean, even if the mean temperature, the global mean temperature, the real global mean temperature, not the temperature at the Earth's surface, but even if the real global mean temperature, also averaged in the vertical, is constant, what we are concerned with is the surface. So any perturbation of the surface temperature is a problem for us. So the mean temperature that maybe can be regulated in some ways, that is even probably more close to be constant even in the global warming scenario, because we have learned that this equilibrium temperature just has another position, but the surface temperature is the problem, and so that's very likely to increase. Yeah, so there are so many problems. I mean, the basics of thermodynamics are, of course, included in this model, the basic of hydrodynamics. But there are so many processes that may be important on those timescales. Cloud changes is very difficult. Of course, we think we understand what determines cloud development on weather timescale, on seasonal timescale, maybe on this timescale. But is it enough to be able to predict the future? There really, and probably there are processes that may be relevant that we don't even know about. Maybe something that you have in mind, I don't know. There could be something we don't know about because we haven't discovered it yet. From this one history, from this one observed history, we were not able to discover this important phenomenon that may be influencing the climate in the next 100 years. What can we do? We can only say, okay, this is what we have. We have tried our best. And
Okay, and when you talk about the 100 years and coming up with a model, will we have one specific model, or we can have two models working?
Okay, yeah. So when I talk about these assessments, that's kind of at the moment going on. Many centers in the world are contributing to this process. So I don't know if you have heard about the IPCC report. So essentially, there are more than 20 climate models being used in this process from different countries. So obviously, the big countries run their own climate models. The United States, Canada, go everywhere in that hemisphere. in Europe, many countries have their models. Asia, many countries. African countries. In Africa, there are probably also some countries who run their own climate models. And they all go together in this pool of estimations. It's a little bit, that could give the impression that there's a lot of independent information that goes into this. That's a little bit tricky because essentially there's a kind of a psychological problem to this. You have seen this number. So these models on average produce this warming of 2 to 6 degrees in the global mean. So the psychological component is the following. You are a researcher in your country. You work in Kenya on such a model. And you find, you do the best, you run your model, a prediction for the next 100 years, and you find your model, my model shows 1 degree only. It's an outlier from all these models. It's underneath. So now you try psychologically. You don't say, okay, this is my result, I give it to them. No. You try to improve your model. Improve, but according to which? According to this truth, which is not a truth, because you want somehow to lie within this spread that other models are getting. Because you don't want to be excluded because of this. Because people say, oh, no, she is not a good researcher. She doesn't produce this number. You are afraid. So you try somehow to change your model in such a way. It may not be that easy possible, but models are very complicated. You may change a very small thing, and oh, you are lucky. You get 2 degrees instead of 1 degree, and you're happy. Okay. So it's very, very dangerous to say that even though every country essentially runs their own simulations of climate, but it's very tricky to say that they are really so independent. Because kind of psychologically, we try, okay, once this has been produced, everyone kind of tries to lie within it. Of course, it's a very critical process, and their researchers have their independent minds, but a little bit of this component is there. So they're not so independent as one may think.
Therefore, working in energy, they say that fossil fuels, if at all they are going to be there, they are giving them a span of the next 50 years. I think after that, they will be done. There will be nothing like fossil fuels. So can we base on that and say, okay, then the emission of carbon dioxide due to fossil fuel burning will be finished?
I think that's if we burn all the fossil fuel possible, I guess that's a safe bet. That would be a good estimate. Let's say fortunately, not fortunately, whatever. What will first happen is that it will be very expensive to get out more fossil fuel, and we will anyway first try to find other possibilities, even though there's something remaining, but it will be so expensive to get it out that already that causes some drop-off. That is probably not so relevant even for the next 100 years, although we may be getting into that limit. But yeah, this is a good point. Unfortunately, by then we have increased the CO2 amount in the atmosphere so much that we are not having doubled the CO2, but maybe 5 or 8 or 10 times even, or 16 times the CO2 concentration, which would be a very dangerous situation. But yes, this is an upper limit. If all fossil fuel is burned, then this is an upper limit. But this upper limit is really high, very high. And yeah, some studies are doing those extreme possibilities, like 16 times CO2 instead of 2 times, 16 times. What happens to the Earth if we increase the CO2 concentration by 16 times, which probably would maybe fit, I just guess, to a scenario where we really burn all the fossil fuel reservoirs. Then probably some of the tropical oceans would almost boil. That's the Earth would become very hot in some regions. At least we have an upper limit, yeah. But that upper limit is really high. It's,
Is it possible to make artificial atmosphere in the lab so we can run experiments?
if we can, sorry?
An artificial atmosphere in the lab.
Yeah, that's a very good suggestion. Yeah, some people in the lab. There are some lab experiments you can do to understand geophysical fluid dynamics. They're typically quite idealized, but there are some things we can do. In artificial atmosphere that behaves like the climate in the lab, it's a very good idea, and there are probably some people who think one could do something like this. At the moment, no one has found the solution, I would say. But there are some things you could do, like changing rotation, letting something rotate that gives you the effect of the Earth rotation, and things like that. You can mimic some of the processes we have. And then it's a matter of rescaling everything to get kind of the right numbers. But in principle, it's a very good idea. But I guess very difficult to realize. But it's that would be a good idea. Also, what people do now with satellites is to look at other planets also, of course. So instead of, we just have one Earth. Of course, there's nothing that is similar to the Earth's climate, but at least we can look at some other planets and what is the climate there. So we have some kind of independent analysis of climate, if we want so, on some other planets that we can observe. So we have some other curves, but they are not relevant necessarily for the Earth. So it's a very big problems, and climate models have problems, known problems, and climate models very likely have unknown problems that we are not even aware of, that something is relevant, that is relevant. So this is just an estimate of how relevant is the increase of these gases. And you see we are very well aware of the fact it's not only CO2 that is relevant. There are other gases that are relevant and that are taken into account into these simulations. So people are very well aware that this is not the only one. But the CO2 seems to be the most relevant gas for changing the Earth's temperature. This is kind of this radiative forcing is kind of an estimate of the relevance of a gas in causing temperature change. And there are some effects that go into the other direction. So this positive direction is a positive radiative forcing, so a warming. These blue colors would be a cooling. So the cloud effect, in fact, would be a relative cooling. So if this is wrong, you see here's an error bar. Estimated error bar. It's not really an uncertainty estimated from these model estimates. And it's huge, you see. The estimated uncertainty is huge. So if this goes up to this number here, 2, almost minus 2, then this offsets completely the CO2 effect. So there's a huge uncertainties in these. And the same is also with aerosol, with the total aerosol. So aerosols have these effects. Surface albedo changes. As we change vegetation cover, perhaps, that has some effects. But at the moment, it's thought that on average, there's this positive, with some estimated uncertainty here. But this uncertainty is, of course, very uncertain again. I just wanted to... as a consequence, because people have realized this, as a consequence for this problem for the next 100 years, people are saying, okay, can I just finish this sentence? Okay, the next 100 years may be very tricky, very difficult, because so many things can happen. What about we do weather forecasts? We do seasonal forecasts. What about we aim for the next decade? We try to predict something for the next decade. Maybe a little bit more realistic. Very difficult also already. Very difficult because we're even interested on shorter timescale variations, which are perhaps more difficult to predict from a predictability point of view in principle. but perhaps, given the uncertainties we have for many reasons, for the maybe a decadal prediction is more realistic also because then we have more samples in our 100-year or more than 100-year observed record. Yes.
Okay, I don't know. Is it possible, like, to predict for the next some period the change in temperature just by looking at the memories of like the brains of animals? I mean, I mean, I don't know, but when they look, I mean, they can, okay, there might be some parameters, some variable, and then they can see, and then they can record in their brain, and then when the temperature changes, this parameter might evolve with them, and then they can still be, I don't know.
I don't know. I don't know. It's for sure that, I mean, animals adjust to climate, like humans probably have adjusted to climate in the history.
Yeah, maybe there might be beta parameters on temperature to look, so that we can have a...
Yeah, I'm not aware of this. It could be.
I even heard that some animals have the ability of predicting the weather.
Yes, this is a belief. Maybe I'm not sure. I know that this is a belief, and for some animals, actually, I believe it if there is a relation between the perception of the animal and, for example, the pressure. So animals, I guess, would be able, like humans, perhaps, are able kind of to feel what is the atmospheric pressure. So an atmospheric pressure is a very relevant climate, and often pressure change comes before the weather change. So that would be a mechanism how an animal or even humans could feel something. But in principle, the models are much better actually in doing this, at least for a few days. But nowadays, maybe not some time ago. So maybe this idea is not bad. I don't say it's bad. Maybe for climate changes, something that happens in animals is a good indicator. In fact, it is used at the moment. Changes of animal population in regions is used as an indicator for climate change. This is true. It's maybe a more robust, integrated measure of a change in climate than the estimates of temperature we have, because the animal behavior really integrates several parameters in a region. So it's not completely wrong to think in this direction, I think. But it has to be a little bit difficult always, critical. Yes?
I want to ask, I want to know with transportation, if we can know when we can see today everything is not going well around the east, okay? With the degradation of ozone push, everything. So I think maybe one day there will be not life on this globe. Okay, so I want to know,
Could be.
I want to know if those predictions can know exactly when everything will stop.
If human life, when human life will stop?
When life can stop.
No, they don't. Well,
And then if if we have some problem, some chance to find after this fashion, because when you can see before there will be not okay. If I can agree in the beginning, maybe there were some animal after the person, and then until now. Okay, I think maybe maybe tomorrow people will disappear. After there will come another.
okay. No, the honest answer to this is yes. Nowadays, an Earth system modeling would probably mean that you try to estimate even that. You would try to estimate the evolution of human population, and probably also, if it is relevant to climate and to the Earth system of animal population, because it could be relevant as by causing increasing methane or other greenhouse gases. The answer is perhaps nowadays models even perhaps try to include these kind of effects. And for sure, if one find a relationship above 40-degree temperature in a region, mean temperature in a region, it's difficult for humans to survive. Yeah, maybe then these models would include a rate that kind of tries to implement this in the model. And for the next 100 years, I think this is not so relevant. But perhaps, yeah, the answer is that models try to include even this nowadays. But I've never heard, at least for the next 100 years, anyone claiming that this will cause an extinction of the human population. But I'm sure you can cause perturbations to the Earth climate that it would make it very difficult for humans, for example, to survive. I don't know. But humans are very, with technology, maybe you can build whatever you can imagine, a refrigerator to live inside or something like this. So it's very, technology has advanced a lot. So even if the Earth climate in principle is very difficult, maybe for humans somehow find a way to, I don't know, it's a very philosophical question. Yeah. Yeah.
I was reading somewhere here, and they were saying that much of the carbon dioxide that is offset into the atmosphere is absorbed by the ocean.
Yes.
Now, how quick are the oceans at releasing this carbon dioxide? Because I would imagine that maybe a time will reach, if at all they spend a lot of time before they have released the carbon dioxide. Maybe the concentration of the carbon dioxide in the oceans will be high, to an extent that maybe when the sunshine comes, it gets inside there, and instead of releasing the radiations to go back, maybe they are kept down there inside, and it is the risk.
Okay, yeah, no. So in principle, yeah, this is an important, the carbon cycle. This is part of this carbon cycle that we have been looked the figure at before. How the ocean interacts with the atmosphere in terms of carbon dioxide and the whole, it's called carbon cycle. Is a very complicated problem, and some models, not all, some models try to include this. And the time scale, obviously, for the atmosphere, carbon is immediate. We burn fossil fuel and it's immediately there. But yeah, the ocean has a different time scale. So circulations in the ocean will need many, many years probably to recycle the carbon that has been absorbed. So, the ocean provides a very long time scale in all these considerations. So it may be that the ocean time scale in this is 10 years, 100 years, or even longer, depending on what process you're exactly looking at. But the CO2 radiative effect is important in the atmosphere. For the ocean, there's another effect which is dangerous. Is the ocean, they call it acidation. So the ocean becomes more acid, and that's not good for fish, for the whole micro web. So bacteria may die, and then fish have nothing to eat anymore, and so we have problems also in the ocean if the ocean uptakes too much CO2 and other substances that are in the atmosphere. So yes, you can invent many things. I just wanted to show you, before we change topic actually, I think I wanted to show you one figure, because we've talked about the distribution of global mean temperature. I hope that you can see something like this. So this would be from this model. This is what they call it, multimodal ensemble mean, annual mean change of temperature. So this is now really from one of these assessments where climate scientists come together, and it's not an opinion, but they compare really their models. And what is shown here is the temperature change predicted for, like a typical time spans is here probably. So that's not even so far. Yeah, here. And this one is like almost 100 years in the future. So 2071. So they average the climate for a 30-year period from 2071 to 2100 and compare it with some reference period that has been from the 60s to the 90s. And they look what is in the mean, what all these models produce, what is the mean temperature change? I think you asked this question. You see, it's in many parts, it looks actually quite boring, if you want to, because it's very homogeneous. You cannot probably read these numbers. But in this scenario, which is something like doubling CO2, close to doubling CO2, we get something like a 2-degree warming everywhere. It's quite there's not much structure to it. Perhaps also because we average many models here, and if models are doing different things, then we average all these different information out. But what do all models show is that towards the northern latitudes, not so much in the southern latitudes, and that's related to the potential to melt the sea ice in the northern latitudes. So we get a much stronger temperature increase in the northern latitudes. So up to, whereas the mean temperature change is maybe 2 to 3 degrees, then in the northern latitudes we go up to 8 degrees. Maybe there are even some regions where we get 10 degrees temperature increase in the mean. That's quite a huge number. But otherwise, it's quite a boring story. And this is anyway, this is quite robust for the temperature. These pictures are quite robust. But temperature is maybe not the most important variable to look at, because maybe we are more interested in rain. Temperature is important, but also rainfall is important for our water resources. And rainfall is a much more complicated picture. Rainfall is not changing homogeneous as temperature, obviously, in any way. Rainfall is adjusting in a very, very complicated way. Somehow predicted consistently by these models, but maybe every model predicts something different anyway, because the processes are very, very complicated. And even small changes in this pattern here would cause huge changes in the rainfall, maybe more than the average increase in temperature. So that's a very complex problem that is in investigation, and every few years climate scientists come together to discuss this. But now we want to discuss something more. I do not want to discuss climate change policy issues here, because here we go into decisions of governments and things like that. What do they rely on? Of course, there's a political process in this. You all heard about the Kyoto Protocol, where governments come together and try to reduce the CO2 emissions. And some governments are against this. Some governments are in favor. And this is a too complicated issue. Alternatives. What are alternatives to fossil fuel burning? There are renewable energies, sun energy, water energy, nuclear energy. Who dares to mention this? Nowadays, it's after what has happened in the recent past, nuclear energy in Europe is not anymore a very near future option, because people are afraid that something may happen. Even if something happens in a country as developed as Japan, then things can happen anywhere essentially. So even though nuclear energy would be potentially a solution to the CO2 problem at least, but it's not politically sustainable perhaps. Well, I don't want to say this because maybe some future development find a possible for completely clean and unrisky use of nuclear energy, and then this could be the solution. Who knows? Yes.
I think learning these things also contribute to how we are seeing now. Because if people didn't learn this field, people would not be afraid of this kind of thing which we are talking about now. So, knowing that industry, people are making some, are producing some CO2 or I don't know, make people afraid and then erase,
I don't understand the point you want to make actually.
The eating of atmosphere eating.
Yeah. You think it's overstated? The problem is overstated. It's not as important as climate scientists.
It's important, but the fact that we know, we learn this field also contributes to these kind of things.
The fact that we learn it
yes,
contributes to the heating.
Yeah, if we didn't, nobody will be afraid of this. But now we know that it's not better. We are now afraid, and for me, I think it's contribute.
I'm sorry about that. I think I kind of understand what you want to say.
Because if people didn't know about these things, life
we would all be happy.
we will not care about.
But then my answer would be: do not study physics.
No.
You would be a happier person not studying physics, not being interested in why things are as they are.
Okay, if I didn't know about physics.
What is your interpretation?
That we should educate people to be aware about what we are facing.
Yes.
But when you educate people, you have more powerful tools. Because if for example, the president is against reducing CO2, but people can force him to reduce it. Then you have education, people will know what is going on. So
Yeah.
it's saying for us to know that that's our way to contribute to reduce CO2, to make people aware.
Yeah, it's important.
So, knowing this
Thank you.
also
Yes.
make our system very hot.
The discussions are hot.
It's like
The discussions are hot. Okay, I'm not 100% sure I understand where you want to go. I mean, one thing is true, for example. Like for these IPCC meetings, the scientists meet in some places. In order to get there, people have to get into airplanes, fly there, and use fossil fuel. People have conferences on climate change, get to some places and discuss about climate change. By doing that, by getting there, you use probably more fossil fuel. Yes, this is the case. And in fact, there are some conferences now done with personal computers. So you use Skype or whatever with your computer and have conferences, online conferences, without going to a remote place where to bring many people will probably even increase the problem. But yeah, this is yeah, this is a small side on this.
Maybe I think to study about those things. Okay, for humans we are feeling, and there is an inherent fear, right? We don't want to. We want to be as if like the change. In temperature or something may change the state of humanity into other forms like human, and we don't want to be changed. That's why maybe. It's just part of the cycle, and we don't want to change like. And
okay, yeah.
we cannot control this stuff because it's a big thing. And
We have fear. Yeah, no.
just because of fear.
I told you there are people who even think climate change is better for their societies because maybe now Russia or England is able to produce wine, which they have not been able before, and so it's good for them. Or some mosquitoes cannot survive anymore in certain regions, and so it's good for that population. So there can be always, there can be good things to it. I don't want to go into this discussion. I'm really more interested in the physical problem of this.
Please, what is the age of the Earth?
Don't even ask me that.
And is it the right age or
Can we look it up on Google?
yeah, okay.
After this, because otherwise I interrupt it. Dinosaurs died out when? A few million years ago. Okay. Now we come to a completely different story, interesting story, because we are talking about a phenomenon which is one of the few very well understood phenomenon that we are able to describe nicely with the thermohydrodynamic equations. We can understand it, we can try to make predictions, because this phenomenon is on a time scale of, say, years. So it's something that is not unrealistic given the history that we have. We can try to use our observed history to understand it. And it's relevant for seasonal prediction. Because if we can predict, have you heard, by the way, do you all know what El Nino is? El Nino means child, no? Baby. But it's also a name of a phenomenon. The El Nino Southern Oscillation. It's a phenomenon that happens in the Pacific region, essentially, but influences climate all over the world. And it's one of the very few phenomena that if you predict this right, then you are able probably to make a seasonal prediction for what happens in the next few months, which is a very tough business for many regions, for surprisingly many regions. You are able to make a prediction, even though the really local phenomenon, and it's mainly related to changes in the sea surface temperatures of the Pacific region. So it's a very nice phenomenon, a very well understood, very well investigated phenomenon that is relevant for seasonal forecasting that we want to discuss here. That's the reason, essentially, it's very important anyway also, but it's also a very nice, very well understood phenomenon. So we are looking into the tropical Pacific again, and we looked at this already before, and we looked at this figure. So what is happening? We get all this solar radiation. Now we concentrate actually on this basin. The reason why this is the basin where this phenomenon happens is most likely because it's a very big basin. So there's a lot of space for interesting ocean dynamic to develop. So this is the energy, the solar energy input at the surface here, which we have discussed already. And as you can see, here there are these structures, a lot of energy input here because there are no clouds. This global structure is because we have the radiation is decreasing on average if we go to the polar regions. And then there are some changes due to the fact that we have clouds in this region. But there's a lot of solar energy coming into this region. And okay, this energy, since the ocean doesn't heat up on average in the long, in a stable system, it has to be lost, and we have named this already. Of course, there's an emission of infrared radiation, according to the Stefan-Boltzmann law. We have discussed this. There's the evaporation, which causes a loss of, we call it latent heat. So the phase transition from the water phase to the water vapor phase causes a cooling of the system. And there's the direct heat conduction by turbulent motion close to the surface. And the ocean itself, if we now look at not at a global picture, but at a regional picture, can transport heat away, of course. If we heat at one point, we can lose heat also by transporting it away from that point within the ocean, laterally. Okay, this latent heat flux is actually shown here. So it's these positive numbers means that the ocean is losing this heat. And you can see it's a large amount compared to even to the solar radiation flux. It gets orders of magnitudes that are the same as the solar radiation flux that is lost here by this evaporative cooling of the ocean. So it's a very important process. Interesting, you see over land surfaces, of course, it depends where you are. Where there's a lot of rainfall and the soil is wet and you have trees, then you can lose a lot of heat by evaporation. If there's a desert, of course, there's no water available for evaporation. So other processes have to take care here of the energy loss. The infrared heat flux is then determined mainly by the temperatures. And as you can see, for example, in the desert, where obviously we don't have the energy lost by evaporation, we have a lot of energy loss from because the ground heats up a lot, so we get a lot of infrared radiation that goes out from the surface. And yeah, these numbers are smaller though. Okay. Okay, this is quite an interesting map also. So this is if you look at the surface, this is the net energy balance. So if you add together all the energy fluxes at the surface, incoming solar radiation, the latent heating due to evaporation, the heat conduction, and the radiation that is lost by the energy that is lost by radiation, and the picture that you get is this. Obviously, if you average this, so this is the average energy balance at the surface. Blue color means that the ocean gains energy. Red color means that the ocean loses energy. So if you average this up, this number in an annual mean is very close to zero. There can be small perturbations to it, of course, if the ocean on average is warming up or cooling off. That's the average of this. The global average of that would give a tendency for the global mean ocean temperature. But these numbers turn out to be in an annual mean to be relatively close to zero. That means that the ocean has to transport heat from these regions into those regions. So the ocean, as we know, is moving. It's not a rigid body. So it's not heat conduction that is important here, but it's the motion of the ocean that that exchanges the heat between these regions. In the Atlantic, and this is again interesting, in the Atlantic the situation is a little bit similar, but we also find that there's this north-south hemisphere contrast because of this fact that the Atlantic transport energy from the, we have discussed this thermohaline circulation, from essentially almost from the South Pole to the North Pole. So the Atlantic has this kind of anomaly, whereas on average the other basins transport energy from the equatorial to the not equatorial region. But at the regional scale, this is a very complex picture, as you can see. So the ocean circulations have to fulfill a very complex role. What we want to focus on here is actually that there is a huge net energy input in this region. A huge. So the ocean, from the net fluxes that come from the atmosphere, essentially, everything added together, gains a lot of heat here. But the interesting thing is that if you look at mean temperatures, so this is now for a 50-year period, we average all Julys or all Januaries in the bottom, and look at the mean surface temperatures. Of course, the picture that we see, it's warm in the tropics and cold in the polar regions. On average, this is what comes out of the mean energy input is larger in equatorial regions. But what we want to focus on is this interesting detail in the Pacific, where we have warmest water here up to more than 30 degrees in the Western Pacific, and actually quite cold water even on the equator, cold in a relative sense. So we go almost down to something close to 20 degrees here, close to the equator in the very Eastern Pacific. Even though we have a lot of energy input in this region, it's very cold. And it's much colder on the equator actually than it's even in the surrounding. So it's an interesting phenomenon to understand. Why is this the case? And this situation will drive atmospheric circulations and so on. So it's very, even though this temperature change here is from here to there is maybe 6 degrees, but these 6 degrees are very powerful to drive regional circulations in this region. And if we look into January, the situation is quite similar, a little bit changed, but the overall picture is the same. It's cold again. Now it's cold even north of the equator here. So it's on the equator, it's much colder in the Eastern Pacific than in the Western Pacific. So why is that? Can you make guesses?
Maybe
Because of the circulation.
Circulation, yeah, must be ocean circulation. That's what we know. Because from the surface, the ocean gains a lot of heat here, more than here actually. A little bit here, more here than there. So it must have to do with the ocean circulation. But there's more detail to it, maybe.
Okay, maybe.
It is ocean circulation, yes.
Okay, another option maybe. The angle that the radiation hits the surface.
It's not the. It's okay. The reason is. Another suggestion?
I think maybe when the water, that map. Okay, when the water here is heated and it becomes a little bit warmer, maybe because as the water circulates, this water could be pushed to this direction. So the water that is at the bottom of the ocean will come up, which is much colder.
You studied, huh? This is, yeah. Yeah, this is the explanation, actually. So the reason why the Eastern Pacific is on average colder than the Western Pacific is that the climate system of the Earth kind of is such that since the mean temperatures anyway in the equatorial regions are higher than in the extratropical regions, the mean circulation is, or the mean situation is that we have a low pressure in the atmosphere on the equator. So this is the equator, and here's the latitude. We have higher pressure somewhere in the, at let's say 30 north. In this region here, it's around 30 north, we have a higher pressure. So that drives, that's the average circulation. That is related to the fact that essentially very warm air is lighter than cold air, and so the surface pressure is lower. This is the very simple explanation. The surface pressure is lower where we have the warmest air on average. And then we have the higher pressure to the north and also to the south, actually, of course. It's a symmetric, on average, a symmetric situation. This would, according to a very important hydrodynamic force, this would lead to, for the motion, what kind of motion would you expect from this? By the pressure gradient force. From the high to the low. If you have a balloon, there's air pressure inside. If you open it, the air goes out of the balloon. That's from higher pressure to lower pressure. That's the pressure gradient force who gives us this flow direction. What's happening on the Earth is, because it's rotating, and here it's relevant because we are at large scale, we have the Coriolis force. The Coriolis force causes that this is deviated to the right on the northern hemisphere and to the left on the southern hemisphere. So the final flow in equilibrium is something like this. Given the geometry of this basin, this flow indeed tend to move over the water from the eastern part of the Pacific to the western part of the Pacific. So it's pushed over, essentially, at the surface by the flow. The water is pushed over from, let's say, if here's the American coast, it's pushed over from there to there. It cannot be replaced by the Atlantic, for example, because there's no through flow in this region. It's a barrier. So it has to come from somewhere. It comes from the bottom. And as you have mentioned correctly, the situation, this is the mean. We don't see it very well. I tried to click on it. Yeah. So this is the mean situation at the equator in the Pacific. We go here, here's the surface, and here we go to 500 meters deep, and here we are in the Western Pacific, and here we are in the Eastern Pacific. So this is close to the American coast on the equator. So we see at the surface, we see our picture here, is that we have the warm waters in the Western Pacific and the cooler waters in the Eastern. But what is more relevant here is that it gets so cold as we go to the ground of the Pacific. So the water in the deep Pacific would almost be very close to these 4 degrees that is the highest density. So that's obviously a very stable situation if we have the densest water at the very bottom. And that's related to very slow, on timescales of actually thousands or hundreds of thousands of years, of very slow overturning circulations, they call it, in the Pacific region. So people believe that it's this cold water. We can go, of course, much further down, and then it goes almost to something that is very close to 4 degrees or something, or even colder, depending on the situation. Because salty water then maybe can have another temperature at which it has the largest density. So this water has been created over hundreds of thousands of years by very slow overturning circulations. And this water comes eventually from the North Pole and the South Pole regions. It goes very slowly down. But for our purposes, for the interannual timescale, this can be given as the mean state of the ocean. That's the mean state. Changes are very, very small. So what is happening now, as you described nicely, is that as the wind are blowing over here, the water is replaced from the subsurface, where the water is very cold. And so we get the situation that this replacing of the water causes this cooling, very effective cooling, even on the equator in the Eastern Pacific. And this process is missing in the Western Pacific. Instead, the warm water is pushed over there. So it's the geometry of the basin in combination with the mean climate we have on Earth. That is, we get more energy input at the equatorial regions and less energy input in polar regions. That gives us this situation which causes it. So it has to be the eastern boundary where we get the cooling, because that's where we lose kind of mass, which has to be replaced by the subsurface water. Very interesting situation. Then the interesting part of this is that this is actually reinforcing itself, because now we have the situation where this becomes a little bit cooler. So the pressure here on average on the equator will be higher than in the Western Pacific, where the pressure is even lower because it's very warm. And this situation on the equator, where the Coriolis force is actually not acting so strongly directly on the equator, pushes even more, so increases the pushing of the water from the east to the west. So we call this is again a positive feedback. So the general geometry and the general climate gives us the situation, but then there's a positive feedback even reinforcing this state. But this positive feedback is also can turn into a negative feedback. Yeah, we have discussed these figures already. That's not what we want to discuss. Yeah, so now we want to discuss what is El Nino. So here's some definition from the American Weather Service, essentially. So El Nino is the disruption of this ocean atmosphere system in the tropical Pacific, which has important consequences. So if this is the mean state, then El Nino is a disruption of this. And as you can imagine, since the mean state is cold in the Eastern Pacific, El Nino is a situation where this whole system breaks down and the whole Pacific is covered by the warm water. So in terms of an anomaly, we call it anomaly situation, is that the Eastern Pacific is warm in an El Nino state, which is kind of, in some sense, from a radiative point perspective, more the normal situation, because we expected that to be warm. But given the dynamics of the system, that's not the mean situation. So how do we measure it then? So this El Nino, and the name comes from the fact that in South America, this has very strong impact on rainfall, on regional climate. And this phenomenon is strongest in winter, in let's say DJF, so during Christmas time. And so people in South America have called this El Nino because it appears during Christmas time when the child was born. And so the measure of this is if the sea surface temperatures in this Eastern Pacific region is warmer or colder, in the case of El Nino, warmer than half a degree than the average temperature there, then it's called El Nino. It has to last for some time. La Nina is the opposite. So people think it's not 100% closed, this discussion, but more or less. it's kind of an oscillatory phenomenon. So there's a situation where this system breaks down, and there's a situation where the system is actually reinforced. And so La Nina is this opposite. La Nina name is just to have something opposed to El Nino, so they called it La Nina. It's called the opposite situation where the Eastern Pacific is even colder than it is on average. So the winds are even stronger in the Pacific to push over more warm water to the west and to cool even more the Eastern Pacific. That's called La Nina, and then that's when the surface temperature is colder than normal. And so yeah, here's a summary of this situation again. What's happened in the ocean and what happened in the atmosphere during La Nina, which is kind of similar to the mean situation, where the ocean by the winds is driven from the eastern to the western Pacific, and it rains in the western Pacific, and then we have some kind of an atmospheric circulation that closes this cycle from there, that is reinforcing. This is the positive feedback if we look in this window from this. So it's a positive feedback. But now what happens during now what happens in El Nino conditions? In El Nino conditions, these winds, we call it trade winds, are weakened. The warm water is not anymore kept in the western Pacific, but flows back to the eastern Pacific and is warming the eastern Pacific, and we get this anomalous warm water in the eastern Pacific that influences climate all over the globe. And the reason why this happens so often is that this positive feedback that we are talking about here acts also in the opposite direction. So once we assume you have created a small temperature perturbation in the eastern Pacific, that would weaken a little bit the winds. That would reinforce this positive temperature perturbation, and so on. So this positive feedback in the Eastern Pacific that causes actually the water to be very cold can also act in the opposite direction. Any small perturbation may amplify, and that's called Bjerknes feedback. Bjerknes is a very famous meteorologist who has thought about this positive feedback mechanism, and it works in both directions. It's a positive feedback. So this positive feedback would cause any small perturbations that you insert here, maybe by chance, to grow. Of course, then there must be negative feedbacks. And the negative feedbacks are actually, researchers believe that this is, it's quite sure in this case, it's slow ocean processes, slow ocean waves that are triggered by this phenomenon, that then, because ocean waves are slower than the atmospheric positive feedback, that then slowly causes this phenomenon to change its direction. May turn it even around. These are just rainfall anomalies during an El Nino event. So even though, so this is a typical rainfall. So the 1998 was the strongest El Nino actually that had been observed in the past history. And during this El Nino event, this is the rainfall, the anomalous rainfall that has been observed. So as you can see is this the total rainfall? Yeah, this is total rainfall actually. Anyway, the typical situation is that it's quite dry in this region. But during this year, the rainfall was actually less in the Western Pacific and much more in the Central and Eastern Pacific. So it's a huge perturbation to the rainfall. Very important for rainfall. And this is a typical map for the same year, I think, but here in August of that year when this El Nino phenomenon developed, of the anomalous sea surface temperatures. And as you can see, this is just if you look at the temperature of this event minus the average temperature, you get a 3-degree perturbation here. Essentially meaning that the temperature was in that year quite homogeneous across the Pacific. So it's very important phenomenon to drive climate circulations. And people model this. Here's a simulation of this phenomenon using, again, the thermohydrodynamic equations, coupled ocean atmosphere, and you are able to model this. This is actually the surface height that goes along with this phenomenon, and the colors is the temperatures. I think it's a very old model, but still valid to understand this phenomenon, idealized model. Yeah, so people measure this, like to measure this with an index. There are different indexes that people use to measure this. One index would just be that you measure the temperature in the Eastern Pacific, in some region in the Eastern Pacific. That's an index. So we can say in this year there was an El Nino, and in this year there was a La Nina based on such an index. We have to measure things somehow. And if you draw such an index, this is actually a more complicated index against time. So again, from 1950 on, we're kind of confident that we have a relatively good estimate of temperatures, even in the Pacific. You can draw this, and as you can see, there are periods when it's colder than normal, and when it's warmer than normal, typically. So that's a typical time series of this, let's say, of the mean temperature in the Nino 3 region, which is this region here in the Eastern Pacific. It goes up, can be 3 degrees warmer for some period, then goes down again. So what is important to analyze on this? Of course, people analyze this kind of time series. First of all, the length of an event. So when there's El Nino, how long does it last? It can last a few months, up to a year maybe. La Niñas typically last longer. So you can see a little bit. So a few months is the answer, up to a year maybe can be the duration. And what is the typical frequency of appearance? Every few years. So if you do a power spectrum analysis on this time series, you plug that into some numerical code that analyzes this time series, you will find that it's not really a power spectrum peak, but it's something, a small, smooth increase of variability in the range of 2 to 7 years. That's the typical period of this phenomenon, of this warming or cooling in the Eastern Pacific.
Okay, question. So it means when you have an El Nino, the next time it will be from that diagram.
Yeah.
They cannot be two El Ninos following each other. Only an El Nino then and an El Nino.
Oh, look at the here. Maybe there. I mean, typically, if you think of an oscillator, in fact, the most frequently used paradigm is that of an oscillator. Maybe not a linear oscillator, but a nonlinear oscillator. Then you would make that prediction. Yes, once you are in one phase, you know the period, you know that after some time you will go into the opposite phase. That would be a very easy and nice prediction. Unfortunately, even though this phenomenon is well understood, it's probably an oscillatory behavior. It's not that easy, as you can see. Sometimes, yeah. This looks like there have been 3 El Niños consecutively without really La Niña. Of course, the La Niña definition is a little bit arbitrary by a less than zero temperature anomaly here. So you can... If you shift this zero line a little bit up, then maybe there was a weak La Nina between them. So it's a little bit, but it's not that easy. It's not. Unfortunately, it's not that easy. Otherwise, you could easily predict for the next 4 years what will be the climate, because as we see, probably not today, but in the beginning of the next lesson, this has important consequences for rainfall all over the globe. So it would be a very efficient method to predict climate, unfortunately not in Europe, but in many other places of the globe. If we are able to predict them, very difficult to predict, yeah. Another thing that is very difficult to predict. So models are doing this. And after this event, 1998, this was kind of, people have tried to, when that happened, have tried to to predict it with their models. How can we, and if you look at predictions, models are able to capture this event, but the amplitude is a huge uncertainty related to the amplitude. We will look at this, not today, I think. It's a very...
Why is it difficult to predict? Because the process is really long.
The process is quite simple, but still quite complicated. It's coupled ocean-atmosphere phenomenon, and the atmosphere is actually, it may not seem so, but the atmosphere maintains many different wave processes. Only the atmosphere system maintains very complex manifold of solutions that have to be taken into account. The ocean also, and now it's coupled. So it may seem very easy, it's very easy to understand the principle, but to predict actually something may be very difficult because it's still a very complicated system. It's much simpler than the climate system as a whole, but it's still complicated enough. And it's very nonlinear also because all the equations involved are nonlinear. The d by dt, the total derivative of any variable, gives us a nonlinear term in the equation. So small errors typically grow. I may just want to show you one figure. Okay, they're influencing the tracks of storms and things like that. But as you can imagine, people, and this is an old figure, I could find you the figure that is actually produced for this year, but people have made predictions. So these are different forecasting centers that try to predict the behavior of El Nino. Yes, the Nino is some index. What will happen? So they started in 2007 from a La Nina condition and tried to predict up to almost 1 year ahead what will be the state of the ocean. Different models. And here is what you have been asking. Are we able to predict? Most models say that more or less we go back into a neutral state, but there's one model that predicts, oh no, we go back to El Nino. So it's again a difficult problem. Here's another kind of plume of those shorter forecasts. I think here the forecasts are just a few months long, perhaps, and therefore you see all these lines. So what you hope for these forecasts that the observations are kind of covered by this in this range, and you see somehow, since the initialization of the forecast is perhaps close to the reality, somehow these models are able to do that. But if you look at the tendencies, they can be quite wrong. But the reality goes like that, but some models show something that goes like this. So the answer is under this. Also, this problem is currently under investigation. And as you can see from this, or estimate from a typical plot like this, the problem is complex enough for models to almost give you any answer already after 1 year. So, but with this, you can already do something. You can create a probabilistic forecast. You say, okay, most likely from this, if you apply some rigorous statistical methods, you would say, most likely we will have a cooler state still 1 year in advance than we have typically. But there is a 1, 2, 3, maybe 20% chance of a El Nino or something like this. You can use those forecasts in such a way. So it's a probabilistic problem. It's not any more deterministic on these time scales. Climate and weather after a few days becomes more and more of a probabilistic problem and less of a deterministic problem, because we have to deal with large uncertainties that are maybe even based on very small changes in our initial conditions that, due to the non-linearity of the system, grow, and we are not able to predict details of the system anymore after. some time. Certainly not after 1 year. Okay. I think we are done for today. So next lesson we will finish this. We'll shortly discuss about why ENSO is influencing the climate all over the globe. So why it's important. And then I will give a presentation about the global seasonal cycle, just to finish off this course. And then you will learn about the real ocean when Riccardo Farnetti, who is an oceanographer, actually will tell you more about deep ocean circulation. So El Nino is a phenomenon where the ocean is already important, but it's kind of a phenomenon that needs a strong coupling with the atmosphere. Whereas there are phenomena in the ocean that can almost be understood without having a strict coupling with the atmosphere, that are maybe driven by the atmosphere, but do not have really a coupled phenomenon character.